So for today's webinar, we'll focus as much as possible on the practical aspects of seismic refraction surveying. We'll start with a very short introduction to the principles, but we won't spend much time on this, as more details on the theory can be found in existing webinars and materials online. But we will discuss survey design, data collection, good practice, field setup, and then give a demonstration how to set up the ABEM Terraloc Pro seismograph for a refraction survey. So just in terms of the very basics, of course, what we need for a seismic refraction survey is a source, and that can be a hammer, a weight dropper, an explosive charge, or a mechanical vibrator. We need geophones, and for land survey, these very accurately measure the vibrations associated with the seismic waves. And then we need a seismograph to monitor all of the geophones or hydrophones at the same time and to record the responses as the seismic waves reach each receiver. And then a trigger cable or a radio link is also needed to connect between the source and the seismograph. In terms of the waves that we're looking at, well, seismic waves, refraction surveys rely on the detection of the P waves, the pressure waves, or the primary waves, as we call them. This is the fastest wave because the wave motion and the energy transfer are in the same longitudinal direction. And note that the particles within the block here are compressed and then return to their original shape and size as the wave travels through it. In some instances, seismic refraction can also be undertaken with the detection of S waves or shear waves. This wave is slower because the wave motion and the energy transfer are at right angles to the transverse motion. And in this, the particles within the block are not subject to compression, but they are displaced. S-wave refraction surveys use geophones with a horizontal polarization and a source which is dedicated to generating shear waves. So the basic elements of a seismic refraction survey again. So for seismic refraction surveys, it is only the first arrivals that are need to be identified. Each vertical line shown in this image on the plot represents the response from one geophone over time, with 0, the point at which the source generated the seismic wave at the top. The yellow circles highlight the first arrivals on each trace, or in other words, at each geophone. If the slope is constant, then it shows that a series of arrivals have traveled at the same apparent velocity to increasingly distant geophones, and therefore this indicates layering. In the central shot locations, the top 2 layers are visible here. But here in this off-edge shot, 2 layers are visible, but it's likely to be the second and third layer, as there's no geophones close enough to the source here to record the direct response through the first layer. So the reason that we're able to interpret changes of slope in the time distance data is due to an effect called critical refraction. So as the wave travels outwards from the source, a portion of the wave will travel directly along the ground towards the geophones. Meanwhile, a portion will travel down towards the next layer. And when it hits the critical angle, the rays will travel along the faster refractor and radiate energy outwards. At some point, the refracted energy will overtake the direct wave. And this is called the crossover distance. At this point, the refracted waves will be the first arrivals. And because they travel faster, the slope of the graph being plotted will change. And then refraction is governed by Snell's law. So what are some of the uses for refraction? So the mapping of soil and rock properties, the calculated seismic wave velocity is related to mechanical and material properties, and therefore the characterization of the material, for example, the type of rock, degree of weathering, and rippability, is made on the basis of seismic velocity and other geological information. It can also be used for depth to bedrock or water table, fractures, and fault zones. And these have application to geotechnical, hydrogeological, geological, environmental, and mineral exploration. So survey design and shot positioning. So we have what are called short shots, and these are taken very close to the ends of the spread. If the shot is placed at the end, then at the end geophones, then the geophone at the end should be removed first and moved halfway to the next geophone, because this can prevent damage to the geophone from the shot and provide some additional information on the direct wave. The alternative is to set up shots so that they are always between geophone locations. Having short shots on the forwards and reverse then allows for the assessment of dipping layers. Then we have long offset shots, which are placed far enough from the start of the spread that ideally all of the first arrivals are obtained from the deepest refractor of interest. It's often possible to assess the required offset distance using the crossover distance from the short shot result. An example of this will be shown in the practical demonstration. And then we have center shots, which are particularly useful where lateral changes in geology occur underneath the spread. So for example, where intermediate beds thin along a profile, center shots can help to define the presence and the velocities of intermediate layers, which would otherwise be hidden from off-end shot positions. And lastly, additional shots can be very helpful for characterizing areas where rapidly changing conditions occur. Multiple shot positions at regular intervals can be useful when using tomographic data processing methods, as the additional data will help to constrain the inversion. So choosing a source, sources can be split into three main types: explosive, vibratory, and weight drop. Here are some typical sources and approximate depth ranges. So sledgehammers, these are cheap and simple, but limited on reach. We recommend a polyurethane plastic hard plate as opposed to a metal one, because they give a better source pulse than a traditional metal plate. The buffalo gun uses shotgun shells to create a small explosion with the barrel of the unit pushed into the ground. These are lightweight and portable, so they're good for sites with limited access, where a little extra energy might be needed. Vibration units allow a range of frequencies to mix good penetration with excellent resolution. But please note that in addition to the vibratory sources shown, larger are available with potentially much larger depth ranges. Then we have powered weight drops. These can provide excellent repeatability, which gives good results when stacking or repeating shots to improve the signal to noise ratio. There's a broad range of sizes and energy outputs for these. And then finally, another method of potentially creating a high-powered source is explosives. However, this will clearly be limited in many countries by legislation surrounding the purchase, storage, and use of charges. And lastly, marine sources, which vary in size, ease of deployment, frequency, and depth capability. The one shown is a small boomer type source and is good for nearshore surveys. Another consideration, well, there are many when making a choice of source. We have to consider the cost, repeatability, efficiency, portability, size, safety, and environmental impact. In the engineering geophysics sector, which I'm most familiar with, it's often the case that much can be done with a hammer and signal stacking where needed. This is because the depth of investigation is usually relatively shallow. Hammers are highly portable and cheap to use, with little or no environmental impact. And this means that if they can be used, then they are usually the preferred choice. If it's clear that a larger source will be needed, then the next size up in terms of energy output will be either an explosive or a weight drop source. However, it can be seen from the comparisons opposite that in addition to considering the overall energy output of the source, the bandwidth affects the ratio of signal, affects the ratio of energy useful for refraction relative to the ground wall. So note that in the example in the bottom right figure, at the very, very bottom, it shows that Burmex produced about 1 order of magnitude energy more than 136 kilogram weight drop, but only incrementally more refracted energy. Most of that extra energy is ground roll, which for refraction is perhaps not so useful. Also note that in the above example, that when grouping weight drops in general, They are producing a noticeably more reflected and refracted energy and less ground roll in relation to the smaller grouping of explosive sources, despite the fact that the total energy output is similar. When choosing geophones, so the construction of a geophone is a cylindrical coil of wire wrapped around the magnet. As the geophone moves relative to the magnet, a current is generated, and then the current itself is proportional to the acceleration of the magnet through the wire loop. A range of geophones may be used. Spiked is most common and applicable to soft ground. The tripod type can be used for refraction surveys on hard surfaces. And then we have also 3-axis geophones for measuring different components of ground motion. Typically for refraction, 8 to 14 Hertz geophones are used. Geophone sensitivity rises as it gets up to its natural frequency. And then most geophone types produce a flat frequency response up to their spurious limit. And because the Earth itself acts as a low-pass filter, attenuation on higher frequencies increases for larger arrays with greater source offset distances. So the performance of a certain set of geophones will then be dependent on the bandwidth of the signal that reaches them, rather than that emitted by the source itself. Topographic considerations. It's necessary to record topographical information for geophones and shot positions to allow accurate calculations when undertaking seismic refraction. Often this is done with high accuracy RTK GPS, but in areas where RTK isn't readily accessible, then robotic total station can be used also. Next, just a few general procedures that help to keep things from getting messy on site and ensuring you get the best data possible. Keeping cables to one side of the survey line avoids trip hazards, and cables not if they aren't in loops, then that's a good thing also. Receivers and sources need to be well coupled to the ground to ensure the signal can be transmitted with as little loss of energy as possible. Coupling of the geophone can often be improved where superficial deposits are loose by digging down a short distance, and this can also help to minimize the noise associated with wind and rain. So having a small shovel or trowel is a good piece of equipment to keep with you in the field. And applying pre-triggers to the preset in the seismograph will allow you to assess the repeatability of the trigger, and that's good for quality control. And finally, when placing our geophone spreads, avoiding areas of poor ground or standing water can be very important to avoid poor coupling or noise within the seismic spread. So where possible, intelligently adjusting the position of the spread will significantly help the data quality. And then another point on data collection good practice is the annotation of field records. Field records to relate stored seismic data on the seismograph to field observations and the type of test being undertaken will help to ensure the survey organized and minimize errors during post-processing. Field records usually keep notes on the following: repeat readings, checks done, tests carried out, the position of the shot, the number of stacks, the ground and weather conditions, and then other metadata including the time, date, spread location and orientation, receiver spacing, and file number. So for each setup for refraction, it's usually quite a simple procedure. We set the instrument down at the center of where the spread cable will be. We decide upon which way the spread will run. Takeouts where geophones attach on each spread cable are numbered 1 to 12 for a 24 channel or 1 to 24 on a 48 channel instrument. The convention is to have the numbers increasing sequentially along the profile. We then lay the cables each side of the machine, keeping them straight, usually with the aid of tape measures. And then we remove the dust caps and attach the first cable to the connector panel on connector 1, and the second cable to connector 2 on the lower part of the connector panel. And then we interlock the dust caps from the machine and the cable ends to avoid dirt or moisture ingress. We then insert geophones adjacent to each takeout, push them in firmly and keep them as vertical as possible, and then connect them to the cable. We then, if we're using a trigger cable, connect this to the analog trigger input and then run it out to the first shot position and connect the trigger geophone to the cable drum, or if it's a hammer switch. And then if we use an external battery, we can then connect this and then switch it on. And we're ready to begin. So for the practical demonstration, I'd like to show how to set up the Terraloc Pro 2 interface for refraction, how to check the data in the field. The data that we will show in the demonstration were collected using a 48-channel instrument along linear arrays with 1 meter geophone separation and a hammer source. The expected depth to bedrock, the target in this survey, was from a nearby borehole at 5.2 meters. If I jump in. So I've now logged into Terraloc using TeamViewer. So you should all be able to see the Terraloc screen. This is the screen that greets you when you first turn on the instrument. It loads up into the SeisTW software and it brings up a wizard. The wizard mode is designed to allow a user to quickly set up the instrument for a certain type of measurement by offering sensible suggestions on the settings that are used. So the first thing we can do, if we run through the wizards, which I'll show, and then go in through more detail on the individual settings. We have the number of channels. This is a 24-channel instrument, so I'll select 24. And then we have the option to select the type of measurement. So we have options between refraction, reflection, MASW, and then marine surveys. I'll leave this on refraction. And for refraction, it suggests a record length of 512 milliseconds, which I'll leave on default at the moment. But if you wanted to, you could change it here or later in the settings. We just tab across to the next option, go to the next screen. And here we have the option set up our array geometry. Here we can enter our geophone spacing, our energy source, which I will set to a hammer source. And again, this is also adjusting the settings that are used for the acquisition. And then we can change the units. If we want to enter a geophone spacing of 1.5 meters, that can be done, but we would select centimeters from the units here and then enter a value of 150 centimeters. That's because this geophone spacing option here will only accept whole numbers. So I'll leave this on 1. And then the option below is the array spread cable orientation. So by default, it is set up between with increasing numbers from left to right, which is the convention used. So as long as your takeouts on the ground are matching this setup, then it should be set up correctly. Some people like to have both of their cable reels at the center of the spread with the instrument and then pull the cables out from the center to the end. And then that would mean that on one side, the numbers are increasing and then they get to the center and then they start decreasing again. So that's okay to work that way, but you just need to remember to flip the relevant cable so that everything matches up correctly with what's on the ground. And then we have the option to set our trigger position. So I'll leave this on 0, but we could have this at minus 8 meters if we want to have an off-end shot to start with. And then we can also enter in an increment value. So every time a shot record is saved, the trigger position will then update itself by however many values we put in the increment. Just want to double check that I am sharing the screen properly. Should be. Okay. So we press OK. And then the instrument loads into our main acquisition screen, which is our shot record, shown currently highlighted, the large blue image. I'll talk through that in just a moment. But first, I'll just go through the acquisition settings and the general setup. So when we start a survey, the first thing we would want to do is usually change our working directory. When we start a new survey, it's helpful to have all of our files saved in a new folder, and then they're easily accessible and organized. So we'd enter our file tab, and I'm controlling all of this just with the keypad. So there's a few shortcuts that you'll need to know. To access the top toolbar, it's just the Alt button and the space together, which highlights a value in the top toolbar. And then we use the left and the right arrow keys to scroll between the different menus. In the file menu, I can go to change working directory, press enter, press up the up arrow, and then go back to our root folder, which is size TW data. Press enter. Create new folder, and then I'll call that today's date, which is 17th of the 11th, 22. Press enter to go into the folder, enter again to open, and now everything that we save will be saved into this folder for us. The next thing we might want to do is go into our preferences tab and set up our file numbers. So file numbers increment each time they're saved, which means that when we start a new survey, it might not start from file record number 1. But if we want to do that, we can set this in our preferences here. So if we go back to 0001, we also have options to save data formats or change the data formats in here. That's okay. Okay. And then in our setup menu, sampling, trigger, noise monitor, filters, receiver spread, layout geometry. This is the area where we can go to set up our survey in more detail or change values that we might want to adjust based on our own understanding of the site or tests done at the site. So if I first go into the sampling, by using the wizard modes and selecting refraction, it's updated these values for us. So it's suggested that we use a sampling interval of 1000 microseconds, which is 1 millisecond, which relates to a sampling frequency of 1000 hertz. So value frequencies up to 500 hertz should then be accurately represented by a sampling interval of this value. Here we have another place where we can update our record time. So at the moment it's sampling for 512 milliseconds. But we also have the option to input a pre-triggered delay. I have a default of minus 100 milliseconds. So 100 millisecond pre-trigger, which means the instrument will show 100 milliseconds of data before the trigger was made, because it's constantly recording. But what this also means is that it will subtract that from the recording time. So we'll actually have 412 milliseconds of recording time when we account for the pre-trigger delay. The number of stacks We can leave this on 0 if we have the stack mode on preview, because the preview option allows us to stack multiple times. But the other advantage of it is that it allows us to view the data in a preview before we choose to add it to the stack data. So that gives us the option to reject bad data from the stack. Because once data has been accepted into the stack, it's added the data to the existing data, and then you can't just unstack that or remove it afterwards. So it's this is my preferred method. So I'm going to show the data acquisition using the preview stack mode. Rearm is manual. Input voltage range. So this is the this is set up for land geophones, which generally are quite small voltage. There's options to change these if we're using hydrophones or marine surveys. But again, this is one of the options that's updated by choosing refraction on the wizard mode. So I'll quickly run through the trigger. By default, it's set as analog, which is what we would use for our trigger if we're using a trigger geophone. We can change it to make break if we have a hammer switch, or if we have digital triggers, we can use the TTL, or we can trigger based on channel or using a manual trigger. So I'll leave this on analog. And if you're working with analog, then you have the trigger input level, so you can adjust the sensitivity of your trigger based on whatever trigger you're using. And then below that, we just have some options for setting up the digital triggers, and then the option to add in some warnings. And I'll show on the next screen where they would be applicable for. So if we tab along to the next one, the noise monitor, by default, that's turned on. That means that a noise monitor will show up when we activate or arm the instrument. If I press the show noise button, this is the view that will appear. Using the plus and minus arrows, we can adjust our threshold value. So if we reduce this value, when it goes into the noise floor, we can see that the threshold alert activates. So if on the previous page, on the trigger page, we have selected to activate some of the error warning messages, then this is one of the warning messages that we can adjust for the point at which a threshold alert will appear for noisy geophones. Things like that. Then we have one more page to go through, which is the filters page. Here we have the option to add in notch filters for power line frequencies. So we have 50 and 60 Hertz options. We also have the option to apply an analog filter. So this is turned off by default. A lot of people that we work with would generally prefer to not have any analog filters, collect unfiltered data, and then filter in post-processing using digital frequency filters, because they have the advantage that if you want to remove the filter and go back to the raw data, you do have that option. Whereas with analog filters, these are applied at the time of data collection. So a data that's been applied in the field using an analog filter cannot then be reverted back to the unfiltered data during post-processing. And then we have some options for removing DC offset from tracers. So once we've set up all of our parts, oh, there was one other thing I want to show there. In all of these, at the bottom, there's the option to save and load. So if we set up our instrument either in the office partly or on site through testing, and we have a set of optimum parameters for our survey, perhaps we leave the site and come back at a later point, or perhaps we have a lot of work at this particular site, or perhaps we want to send someone else to go to site for us, but we have certain settings that we recommend. What we can do is set up all of our settings on the instrument, go to the save option, And then we can save an acquisition script file which stores all of those settings. So if I create one using today's date again, and just save that into the working folder, there we go. Then it's just a case of someone setting the instrument up, turning it on, and then using the load option to then load in those acquisition settings again. So once those have been set up, and at this point we're in the field, we've got our geophones laid out, we've set up our acquisition settings, we're ready to go. So what we're looking at on the geophone here is, as shown before, we have a vertical line representing the trace for each geophone. We have, in this case, 12 of them. We then get to an orange box, and that represents the relative position of the seismograph within the spread. And then, of course, we have another 12 vertical lines representing the geophones on the second cable. On the left-hand side, there is a red circle. This represents the position of the shot within the spread. We started with a shot position of 0 meters, so it is at the position of the first geophone. And then above that, there's a little green dot. And if I press the tab key, it will then highlight the bottom left box, which is the trace view for the first geophone. And if I use the up and down arrows, I can then cycle forwards or backwards through individual geophones to look at their trace readouts. And that also updates the bottom right image, which is the frequency spectrum for that particular geophone. And you'll see that the green dot moves along to show visually where the data is being viewed from. So if I arm the instrument here, there's nothing connected to it at the moment, but I can trigger the instrument automatically by then pressing Control and Arm again. You can see that the instrument at the moment, there's a message on the bottom toolbar that says armed, and above it, the noise monitor appears. I'll press Control Arm now, and the message saying triggering has arrived, and there we have the data. We can then choose to accept the data, and that it will add it into the stack, or reject the data. So I'll accept this, assuming the data looks okay. And then it's rearm the instrument, brought up the noise monitor, and then we have the option to stack again. So Control and Arm. And now in the bottom left, we can see record 001, S equals 2. So this is the second stack. If we reject this, say it was a bad shot, we weren't happy with the responses from the geophones, maybe there was some noise, we could press the reject button, escape, and you see then in the bottom left that S equals 1, so the stack has reverted back to the first stack. So I press escape, there we go, it's disarmed it, we have one stack. If I press save now, then it will create the file for this shot position for the data that's shown on the screen now. So press save, and the record number on the bottom left is incremented to 0002, and the stack number has reverted back to 0. If we had entered a source mover, this would have then incremented the source position. You can also do this in layout geometry. You can set the source position and the source move ups. So if you have, if you're not moving up by a set spacing at each shot position, then you might want to manually input your source location each time. If I change that to 4, that's okay. You can see that the red circle indicating the source position is now moved up. And the other thing, before I go and show the test data, is if we were doing a rollup, another option that's useful is setting our layout geometry correctly for the rollup. So we don't want to be manually typing in the new position for each geophone. What we want is to do that automatically. So if we go to rollup layout geometry again, and if we tab down to our table view, what we have the option here, we can see the current position of all of our receivers. So geophone number 1 is at X position 0, and geophone 24 is at X position 23. If we're doing a 50% coverage roll along, where we leave half of the geophones and we pick up half of them and move along, that will mean that we're moving 1 cable's worth of geophones from the start to the end position. So the way that we can then represent this on the seismograph is just by pressing the space button here, and this brings up a little layout helper. And we can tell it, okay, our new X position for the first geophone in this new spread is going to be at, in this case, 12 meters. Our receiver separation is 1 meter. That's okay. And then it's going to update our X positions from 12 to 35 in this case. And then we can continue collecting data either in a different folder or continue as we are to create one long profile. So that's all the basic functionality I wanted to show in terms of setting up the instrument for a refraction survey. Now I just want to quickly go through a little bit of the test data so that we can really talk about what we're looking for when we're analyzing the data on site. So if I go to File and then Open, and then back to SeisTW data, and then I save this data in the examples folder under seismic data, setup 1. So the first one was off end, the second one was off end, and the third one should be roughly the off end, the on end shot position. So I'm going to open this one first. Okay, so here we have, I can show you, I go to source receiver locations. You can see here that the shot position for all traces is minus 0.5 meters off end. So it's effectively an on end shot position. So let's say we've collected our data at this point and we want to analyze it, if it is suitable yet, or if we need to stack more data. And really the essence of this for refraction is to know, have we got a clean first break? Because the quality of the result is going to be wholly dependent on how accurately we can, or if we can, pick the first arrival that's at the geophone. That's the main thing that matters. So the really important thing with the seismograph is knowing all of the different ways that we can scale and view our data so that we can actually make that assessment in the field. So there's a couple of ways that we can do this. The first way, if we want to kind of rescale and resize the data in the shot record view, which is our main one, we can use the toolbar along the top. So the way to highlight and work with this data, if you're only using the keypad, is to use the Alt and number pad to highlight. So Alt and 6 highlights the variance. So if I then press the space bar, I can change this to a negative. So this just changes the apparent polarity of the waveform as so. If I press Alt and 6 again, we can switch to a wiggle view. If I press Alt and 6 again, it highlights that top view. And I'll just go back to variability positive. The time compression, so that is highlighted by pressing Alt and 7. At the moment, we have an 8 times compression. Perhaps you want to maybe drop that down to a 4. And as you can see, that elongates all of the time arrivals. And that can be very useful for assessing first breaks. The more bunched up they are, the harder it is to actually see if there's noise on the first arrival or not. So, and it can also be better when we're using the velocity analyzer to assess what the apparent velocities are. And then we have Alt and 8 to change the scale factor on the data. That's on 2. But again, increasing this will amplify also the noise and perhaps allow us to better see if there's noise. So adjusting this up or down can be useful depending on the site that you're on and the amplitude of the responses. And then finally, we have the trace clip option, Alt and 9 to highlight that. And that's just clipping the traces in the event that they're overlapping with adjacent traces and making it difficult to see what's going on. So we can do that. And then we also have another shortcut, which is Control and 0, and that hides our trace and frequency view and just allows us to see a bit more of the shot record. So again, this can all be useful during acquisition when you want to see as much as possible of the data. So that's one way to view the data. The other way that is quite useful is if we highlight the trace view, and then if I use the plus and minus arrows, I can bring up this little vertical line. So I'm going to place this where I think the first arrival is, about here. And the trace view, again, that will be rescaled along with the shot record view when we're using those menu buttons along the top. But cycling through this, again, can also be a very good way of looking at the quality of the data. So at the moment, I'm on trace 4, trace 5, trace 6, trace 7, and we can see our arrivals getting incrementally later. I'll go back to where the first arrival is. And at the moment, you can see that there's still a nice, there's some noise early on in the signal, but before the first arrival, it's a pretty clean first break. Okay, later. First arrival there. So we're on trace 27, 28, 29. So at this point, the noise is starting to affect the first arrival slightly. You can just about see it, but at this point, it's a bit hit and miss as to whether we're actually getting a very accurate first break on some of these later traces. So this is why it's good to look through these views and then decide based on the quality of the data here, whether we need to stack more or change something in our acquisition setup. Because here at our trace number 48, you can see that the first arrival is probably around here, but it's a little bit obscured by some noise. It might be possible to clean that up with some filtering in the post-processing. But equally, it's of course better to get good data initially on site, and then it makes life easier for processing the data afterwards. So we've covered rescaling the data. The other thing was how to calculate the long shot distance from the short shot distance. So this is our short shot data. So really what we're interested in is having refractions fully from our refractor of interest. So probably the easiest way to show this is if I bring up the velocity analyzer. So Control +8, that brings up the analyzer. We can then move that up and down the screen using plus or minus arrows, and left. Okay. So we can move it left and right on the screen using Shift and plus and Shift and minus. So if, say, we decided that our breaking slope was somewhere around here, might be a bit later. What we would do is calculate, add up the number of traces to the left, where we are seeing the arrival of what we assume to be either our direct wave or our intermediate layer, and multiply that by our receiver spacing. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, where our spacing is 1 meter. So if we were to begin our long shot 16 meters before this position at minus 16 meters off the end of the spread, that means that all of the shots, the incoming refractions from the first geophone are going to be from that deeper refractor that we're interested in. So that's one way of isolating it. The other thing that we want to do is actually check our velocities, our apparent velocities, because that's what will allow us to at least get an idea of whether the refractor that we're looking at is the bedrock or not. So this can be done with the velocity analyzer that's shown. So if I go first to our first geophone, our first trace, and center the velocity analyzer over the first trace, and then we want to change the apparent velocity using control down. So we just want to make sure that the straight line of the velocity analyzer is going through the first arrivals. And again, this is one of those things where it might be easier. So we've got a time compression of 4, but if I were to change that to 2, for example, it might actually make it a bit easier. So let's try that. I would have to save this. Time compression 2. There we go. So now we've elongated our traces. So actually the velocity analyzer will probably work a little bit better on this view. So control and 8. So perhaps there's something on the top, it's showing the velocity. We change the units to meters per second. So 546 meters per second was the apparent velocity for that position. And then we could do the same for one of the refractors along the bottom. And I tested that before. I think it came out about 2,500 or 3,000. So because it's weak mud rock, it's probably a reasonable velocity for that. So we can assume that we're hitting the mud rock layer boundary there. I think that's everything I wanted to show for the setup and kind of manipulating the seismograph to kind of show you the data in the way that you want. So I'll just go back to the slideshow now, just to do a quick summary. So just in summary, there's many steps that can be taken in the survey planning stage and during acquisition to ensure that the relevant data are collected to the best quality. allowing time to complete these steps will make data processing and interpretation simpler and increase confidence in the end result. And becoming familiar with the keypad shortcuts does allow users to operate the Terraloc Pro 2 efficiently without a keyboard or a mouse connected. And I've been putting together a short list of the shortcuts. So if you have a Terraloc Pro 2 and you'd like a copy, please get in touch. I think that concludes the demonstration and the presentation for today. So thank you for listening, everyone. And I think we're just about on 10 p.m, but I'll hang around for a little while. If there's any questions, I'll try to answer them.